Hello! In this video I will show you how to experience machine learning fault detection on your seismic project. Look how the tool works on open dataset. Here is the well-known EFramework block seismic data. We can see the faulting structure. Here is the Carry 3D. And this is the Apunaki dataset. My name is Ruslan, I'm the CTO at a software company that develops commercial machine learning solutions for the oil and gas. We also have the fault detection as a part of our toolset in Geoplot AI. Our machine learning models are constantly improved by a great team to achieve the highest benchmark scores for the benefit of our customers. Today I will break down what you need to run open source machine learning fault detection on your seismic project. To give you a reference point, the fault detection is integrated as a module for the EFramework application, which is built by me to democratize the use of machine learning applications in our industry.
The first thing that you need to do is to visit my GitHub account and look for the repository called EFramework. It is right here. There are a lot of information about the repo is presented here. Here is the video that will take you through the motivation of creating this repo. Here you also see the future machine learning applications that will be integrated into the framework. Then you should follow the instruction of installation. There are a few steps that you need to go through. And the final one, on the fifth step, you need to initiate the streamlit framework by running this command. Once you run the streamlit, you would see the welcome page. There are also information about the development stage, as well as some reference to Geoplot AI software. Alright, let's go into importing the seismic for our tutorial.
I'm taking here a Carry 3D dataset, which you can download directly from SCDU wiki site. The link in the description.
Then I copy path to the segue file and pasting it into the framework. And we will see the header section.
And there is a problem in here because Carry 3D dataset does not have the inline and xline data in the correct byte numbers.
We need to change that. And everything works fine right now. If you don't like the grayscale, you can change the color map here. You can enlarge the image by clicking here. And let's go into the machine learning fault detection module in here. There is a FaultSec 3D implementation that was authored by Xingming Wu. There are some links that you can't go through. There is a paper that you might read about the method, and also a GitHub account that was integrated as a module into the EFramework. I also copied the abstract in here for your convenience to read it through. And here are a few of my videos about the topic that you might take a look into. Of course, you know that each machine learning model requires its own unique dependencies. There are two versions that you might use, the GPU version and CPU version. Alright, once you install the dependencies, we can go into the app. As you might be aware, we did not load any information into the RAM itself. Everything is stored in your SSDs and HDDs. And machine learning models requires us to have the information in the RAM to get it running. And because we don't need to compute the fault detection on the whole volume, in the next step I'm selecting the range for the inline, xline and the time slices. I'm selecting the time from 0 to 700. Pushing the submit button, it will recalculate the volume and load it into the memory. And take a look here, before the cropping, the number of samples was 1200. And after cropping, it's 700. That is loaded into RAM.
Now we have the data that is prepared for the machine learning solutions to work with.
Here you can see a lot of weights that is available for you for fault detection. But here is the problem. There is no weights in the folder. So you need to follow the link here to the author's Google Drive and download all the weights from there and then pass them into the modules folder. After that, you need to rerun Streamlit app. You would see updated list of the weights in here. You can try out different ones and see which one you like the most. For example, here I'm taking the weights called pre-trained model, and we can see that inference process is starting and there are 147 patches, and you can also see the estimated time to finish the prediction, and it actually goes really quickly in here.
Because oil and gas content is not trending on YouTube, I would appreciate your support by liking this video so that it reaches more people.
Alright, we can see the results below. Let's make it a bit wider. Go into the settings, click on the white mode, and everything is stretched out. So that looks better. By the way, you can also change, I think, the color scheme in here. Let's go into the settings and change it to dark. I think it should work. Yeah, so we have the dark theme in here right now. We can go through the slices to see how the prediction works. Everything looks fine. And we can see the faulting originating in here. Let's go into the time slice and we see the faulting on the horizontal direction. I probably will include the button to enforce the aspect ratio, but right now we need to go into the settings and uncheck the white mode in here. So we can see the time slice in more like original aspect ratio. And then if we are happy with the fault detection and we've selected the best weights that you want to use with this volume, we can go with exporting the volume as a segway file or numpy. What we need to do is to copy the path to the folder where we will save the file. Paste in here, adding the slash and the file name in here, carry 3D. Okay, clicking the save and we can see there is a file pop up in the Explorer. And we should wait for the exporting process to finish. So saving segway file complete. Okay, now we can check the file that we've saved. Copying the path to the file. Once it's read, we can go into the importing the file. We have the same problem as the original segway file. We need to change the inline and byte numbers here. And we can see that the original sample size preserved. And faulting looks okay as we've seen on the prediction. And we can see that the file is filled with zeros outside of the subvolume that we've chosen for the computation. Going through the Z direction, we can see the slice in here. We can enlarge the image.
A tutorial would be incomplete if I didn't go into details how neural network was trained, which architecture was used, and how it was validated. I have video on the channel that goes over the paper in great details. Here is the video.